Now we will solve one example related to the coplanar concurrent force system and one example related to the coplanar non-concurrent force system for our better understanding. So let's take an example for coplanar concurrent force system. So our objective for this example is to find out the resultant, which includes the magnitude, direction, and the point of application. So let's take one example. So I am having one body. Suppose the block resting on a surface, and here we are having the two forces which is acting on it. Suppose the 10 Newton, which is making an angle 30 degree with the horizontal, and second force which is the 5 Newton force, which is also making an angle 30 degree with the horizontal. And now our interest is find R. So R means that is resultant we have to find for this coplanar concurrent force system. So in R we have to find out magnitude, we have to find out direction, and we know this coplanar concurrent force system, so there is no need of finding out point of application because the point of application for the resultant force will be same as the point of application of 5 Newton and 10 Newton. That is nothing but a point O. That is nothing but the concurrent point. So for finding out the resultant force, first we will define our coordinate system. For 2D problem, we are having the coordinate system x and y. And here we are dealing in a vector quantity, so we can say that it is this one is positive x, this one is negative x, this one is positive y, and this one is negative y. So the first step is we have to find out algebraic summation of all force component along x direction. We are interested in sigma summation of fx in horizontal direction. So we have to take component of 10 into this direction, this horizontal direction. So it is nothing but 10 cos 30, and if you see the direction, it is in positive x. So the sign of this component will be positive. Similarly, we have to find out the component of 5n in the horizontal direction. It is nothing but 5 cos 30, and if you see the direction, it will be in negative y direction, so the sign will be negative. So now we can easily find out the algebraic summation of components of all the force about x-axis. So it is nothing but cos 30, that is, or we can say that plus 10 minus, so 5 cos 30. So 5, the cos 30 value will be 0.87, so it is coming 4.35 positive. It means it is acting in positive x direction. Similarly, we have to find out algebraic summation of components of all the forces about y-axis. In y direction, if we talk the component of 10 in y direction, so it will be in vertically up direction. So vertically up is positive direction. So we are having plus 10 sine 30. Similarly, the component of this 5n in vertically direction, it is in upward direction, will be again positive 5 sine 30. So it will be total 15 sine 30. So 15 sine 30 is 0.5 and it is coming 7.5 is positive. So now by this way we have already calculated summation of fx, summation of fy. For the third step we have to find out resultant r, that is nothing but summation of fx square plus summation of fy square. So we are having the summation of fx is nothing but 4.35 square plus summation of Fy is nothing but 7.5 square. So our resultant will be square root of, if we calculate it, it will come 75.1725. So it will come 8.67 Newton. So by this way we can easily calculate the resultant R. Now direction. So again, first make a coordinate axis, so it will be very easy for our understanding. This is x, this is y, and now we are having r, and here we are having sigma fx, here we are having sigma fy, and this one is theta. So theta is nothing but tan inverse of sigma fy by sigma fx. So tan inverse of sigma fy is nothing but 7.5 and divided by 4.35. So this value will come around 59.90. So by this way we can easily calculate the direction also. And the point of application will be the same point where the two forces 5 Newton and 10 Newtons are acting on the body. So for this coplanar concurrent force system, by this way we can easily find out the resultant magnitude as well as direction. So resultant is coming 8.67 and direction is nothing but 59.9 degree in first quadrant. Now take an example for coplanar non-concurrent force system. And the objective is same as our previous problem, we have to find R. So let's take an example. I am having a body on which the three forces are acting at various points. Suppose this one is 10 Newton, this one is 15 Newton, and this one is 5 Newton. And let's take these points are A, B, and C, and AB distance is 1 meter and BC distance is 1 meter. So we have to find out the resultant R. Our objective is to find resultant R. So our first step, we have to find out sigma fx. So we know our coordinate axes are like that: x-axis, y-axis. This one is positive x, this one is negative x, this one is positive y, and this one is negative y. So sigma fx, if you see all the forces like 10 Newton, 15 Newton and 5 Newton are acting in the downward direction, we can say that along y-axis. So sigma fx obviously will be 0. Similarly, for sigma fy, if we see 10 Newton, 15 and 5 are acting in downward. Downward is nothing but our negative direction. So I will take minus 10, minus 15, minus 5. So it is coming minus 30. The minus sign indicates the forces are acting in the downward direction. Or we can write sigma Fy equals to 30 Newton in vertically downward direction. So by this way we can easily understand in which direction the sigma y component is acting. Third one, R equals to summation of fx square plus summation of fy square. So R equals to 0 plus minus 30 square, so it will become around 30. So R will be 30 Newton in vertically downward direction. So obviously, if you find out theta for vertically downward resultant force, so it will come 90 degree. or we can also get this value by theta equals to tan inverse fy by fx. So tan inverse fy is suppose 30 divided by 0, it will be 90. So by this way also we can get. So we are having two things. The resultant we are having 30 newtons in the vertically downward direction, and direction which is 90 degree with x-axis. It means it is in vertically downward. So now, in case of coplanar non-current force system, finding out the point of application of the force, we have to use Varignon theorem. For point of application, Varignon theorem. So let's again draw the system: 10 Newton, 15 Newton, 5 Newton, say A, B, and C. And let's put our resultant force which is acting in vertically downward here. This is our R. And suppose the distance from A is x. So according to Varignon, the moment of resultant force above A, so R perpendicular distance is x, Rx, and the direction is clockwise. So our convention clockwise positive, anti-clockwise negative, should be equals to moment due to 10 at A will be 0 because perpendicular distance is 0. Moment due to 15 at A, it will be 15, and perpendicular distance is 1, so 1, clockwise positive, plus due to this 5 into 2, it is again in clockwise direction, and we know the magnitude of R is nothing but 30, so 30 into x, 0 plus 15 plus 10, so 30x equals to 25. So x will be 25 by 30. It should come around 0.83 meter. That is from here. So we can say that the point of application of the resultant force will be 0.83 meter from A. So by this Varignon theorem, we can easily find out the point of application of the resultant force in case of coplanar non-concurrent force system. After understanding the force system and the methodology for finding out the resultant force in case of coplanar concurrent and non-concurrent force system, now we are interested in equilibrium and free body diagram. So now we will talk about for equilibrium and free body diagram. So one by one I will take these things. So first I am taking the equilibrium. So now the question is that when we can say that the body is in equilibrium. So for identifying the state of the body, by identifying the state of the body, we can say that the body is in equilibrium. So for the body should be in equilibrium if the body is in rest or body moving with uniform velocity, means motion with uniform velocity. In that case, we can say that the body is in equilibrium. For equilibrium, the necessary and the sufficient condition is that all the forces acting on a body should be zero and all the moments acting on a body should be zero. So the necessary and sufficient condition sufficient condition for equilibrium. First, net force on body should be zero, and secondly, the net moment on body should be zero. So these are the two necessary and sufficient conditions for saying the body in equilibrium. If the net force acting on a body is zero, it means body is in equilibrium. And if the net moment on body is zero, then we can say that body is in equilibrium. These are the two necessary and sufficient conditions. And I have already discussed, like, if the body is in rest or if the body is moving with uniform velocity, we can say that the body is in equilibrium. Let's take an example of body in rest. Body in rest. If the body is in rest, it means net force is zero, net moment is zero. So we can say that body is in equilibrium. Similarly, motion with uniform velocity. Motion with uniform velocity. If a body is moving with uniform velocity, then we can say that it is in equilibrium. But how? So let's take Newton's second law of motion, that is nothing but force equals to ma, and we know the acceleration is nothing but dv by dt, that is rate of change of velocity with respect to time. So we can say that, right, f equals to m dv by dt. But for motion with uniform velocity, v will be constant, so dv by dt will be 0, so f will be 0, so we can say that it is an equilibrium. So by this way we can say that the body is in equilibrium. So now we can say that if the body is in equilibrium, then we have to think in terms of force, net force, net moment. It should be zero, like net force and net moment should be zero for body which are in equilibrium. So let's take two problems for equilibrium. We are interested in 2D equilibrium problem. And we are having a 3D equilibrium problem. So in 2D equilibrium problem, we are dealing with the coplanar force problem. So I am interested in x and y plane only. But in 3D problem, we are interested in non-coplanar forces. So I am interested in xy and also in z. So what are the conditions for 2D equilibrium problem? First, algebraic summation of all forces about x should be 0. Algebraic summation of all forces about y should be 0. Or algebraic summation of moment of all the force about any point should be 0. Similarly, for 3D condition, 3D equilibrium condition, algebraic summation of all forces about x should be 0. Algebraic summation of all forces about y should be 0. Algebraic summation of all forces about z should be 0, because there is one additional direction for 3D problem, and moment of all the force about any point should be 0. So by this way we can analyze the 3D problem. So if the body is in rest or if the body is moving with uniform velocity, means body is in equilibrium. So we can apply all these three equations for 2D problem and all these four equations for solving 3D equilibrium problem. Now I would like to discuss one special case in coplanar concurrent equilibrium. Special case in coplanar concurrent equilibrium. We are saying Lami's theorem. So that is for special case in, we can say that three coplanar concurrent force equilibrium. Suppose there are three forces which are coplanar concurrent acting on a body and the body is in equilibrium. Suppose the forces are P, Q and R. The angle between suppose P and Q is alpha, Q and R is beta and P and R is gamma. That is a special case which we are calling a Lami's theorem. And Lami's theorem is applicable for three coplanar concurrent force which is acting on a body and body is in equilibrium. So according to the Lami's theorem, the magnitude of each force is directly proportional to sine of the angle between opposite two forces. Suppose I am considering P, then I have to consider angle between opposite two forces, that is sine theta. Similarly, the magnitude of Q will be directly proportional to angle between the other two forces, that is nothing but gamma. And similarly for R, that is nothing but sine theta. So by this way, we can identify the unknown by applying the Lami's theorem in a minimum interval of time. But the condition where we can use Lami's theorem, it should be coplanar concurrent force and there will be three forces. Then only we can apply Lami's theorem and the body should be in equilibrium. And with the help of this expression, we can find out the values of P. So it was all about equilibrium, 2D equilibrium, 3D equilibrium and the special case Lami's. Now let's talk about free body diagram. Free body diagram. The free body diagram is very useful in solving the problems in engineering mechanics. So for solving the problems in engineering mechanics, the knowledge of free body diagram is very essential. So first of all, we are interested in the definition of free body diagram. As the name implies, the free body diagram means if we draw the force diagram which is acting on a body, then first we have to free this body from all the connected bodies. Then we have to show the all forces which includes actions and reactions. So free body diagram shows all forces acting on a body isolated from other bodies includes action as well reaction. So in free body diagram, first we have to isolate the desired body from other bodies and we have to show all forces which includes actions as well as reactions. Let's take an example, a block resting on a surface. Block resting on a surface. I'm just representing the block. Suppose it is resting on a surface. So now we are interested in draw free body diagram of block. So for drawing free body diagram, first we have to isolate this block from the other bodies. Other bodies means from this surface. So I am just isolating this block from the surface. Now we have to see what are the forces are acting on. So obviously the block is having some mass. So weight of this mass will always act in vertically downward direction, that is mg, gravitational force is acting on it. This block is in contact with this surface, so there will be a reaction which is acting towards the body, that is surface. So this one is nothing but the free body diagram for this block, where this reaction R and the gravitational force are acting on a body. So by this free body diagram, we are showing the forces which are acting on this block. For our present example, there is reaction as well as this weight is acting on the body. Let's take another example for understanding the free body diagram. So free body diagram of ladder resting against wall. So I am trying, this is suppose wall and this one is floor. That is suppose floor and this one is wall. And suppose this one is a rough wall. This one is suppose smooth. So for smooth, no need of considering friction force, and for rough you have to consider friction force. Suppose coefficient of friction, rough case, that is smooth. And ladder which is having a contact with the wall at point A, and here with floor at this point B, and weight of ladder is suppose W, and length of ladder is suppose L. So now we are interested in free body diagram of ladder. So for drawing the free body diagram of ladder according to definition, first of all we have to isolate or we have to separate the ladder AB from other contacting bodies. So other contacting bodies or surfaces are wall and floor. So first of all we have to isolate this ladder AB from wall and floor. We have isolated. Now we are having a point A and B. So this A point is in contact with the wall, so there will be a reaction. The B point is in contact with the floor, there will be reaction. So reaction will be always normal to the surface. So here normal to the wall, it will come like that. RA, normal to the floor, it will come like that. Now in the problem it is already mentioned weight of the ladder is W and length of the ladder is L. So the weight of the ladder will lie at the center of gravity, which is at the middle of this ladder, which is at a distance L by 2 from both the ends. So you can also represent weight at the CG point, which is at a distance L by 2 from both the ends. Now if we see the wall is rough wall, so there will be friction. So now we have to consider the natural sweeping. In natural sweeping case, the B will go in that direction and the A point will go in that direction. So the frictional force will act in opposite direction. So at A, frictional force will be in opposite direction of motion. So it will be in upward direction and the magnitude will be mu RA. And here we are not considering any frictional force at B point because it is smooth. So there is no need of representing the friction. So by this way we can make the free body diagram for this ladder. Here we are having the gravitational wave. Here we are having the reactions RA. Here we are having the reaction RB. This reaction is due to the contact. The frictional force due to the roughness of the surface, which is acting the opposite direction of the motion because A point will move in that direction. So obviously the frictional force will act in that direction. At B point, we are not mentioning or we are not drawing any frictional force because B point is in contact with the smooth plate. So this one is the pure representation of the free body diagram method.